Hey there, welcome to week 9. We're beginning chapter 5, so chapter 5, part 1 today. And chapter 5 is different than what we've done in the past. Throughout most of the semester, we've been focusing on a couple of specific things, okay? And one of those is solids, or liquids, or aqueous solutions for the other one. And those are treated in one way, but gases are different. And if you read about this, you'll hear a little bit more about why gases are different. And it's primarily because they have variable pressure. So their pressure can be changed. And because their pressure can be changed, so can their volume. So for solids and liquids, our volume doesn't really change. Our volume stays the same for the most part, regardless of what kind of a chamber it's in. But for gases, that's not the case. So things are going to be a little bit different. And I just realized that I forgot my periodic table. So if I need one, I'll have to run and go get one. All right. But until then. All right. So first of all, let's just think a little bit, take a little bit of a look at some of the primary things that we're going to need in chapter 5. Okay, and one of the very important things that we're going to need to remember all the way through is that all temperatures must be in kelvins. Now, sometimes it'll ask you for an answer in Celsius, and if that's the case, then you have to convert to kelvins and then convert back to Celsius. So let's remember that our Kelvin temperature is equal to our temperature in Celsius, our degrees Celsius, plus 273.15. All right, now the second thing is that the units that we're going to use, there's 3 different units that we're going to use for gas pressure. And they are pascals, and, well, this is not really a different one, but kilopascals, and atmospheres, and millimeters of mercury, which are also known as torr. Okay, so let's see how those all link together. Well, first of all, there are 1,000 pascals in 1 kilopascal. Okay, and there are 101,325 pascals in 1 atmosphere. Okay, and there are 760 millimeters of mercury, or 760 torr. A torr and a millimeter of mercury are exactly the same in 1 atmosphere. So you might be thinking, okay, well, what is this atmosphere that we keep talking about? 1 atmosphere is the standard air pressure, or the average air pressure at sea level. And we don't really measure things in atmospheres, but most of our calculations for gases need to be done in atmospheres. Okay, so you guys probably remember throughout the previous ones how to convert, but these are the things that you're going to have to convert for this chapter. Okay. Now, the next thing that we're going to do is we're going to talk about some gas laws. And one of these you've actually already seen before, and we'll get to that in a bit. So what I'm going to do is I'm going to do things slightly differently than how we have it in the slides, just so that it's supplementing the slides rather than being exactly like the slides. Okay, so the first law that we're going to look at is Boyle's law. And Boyle's law exists when pressure and volume are changing, and temperature and number of moles or quantity is constant. And we define all of our gas laws actually in part in terms of proportions, okay, or in terms of trends. So what Boyle's law states in words is basically as the pressure increases, the volume decreases. And this is an inversely proportional relationship. So we could also say that pressure is inversely proportional to volume. Okay, and that makes sense. If you have a balloon of gas and you squeeze it down, it makes sense that the pressure inside your chamber is going to be higher. So as the volume goes down, the pressure goes up, and you could say that the reverse is true also. If the volume increases, then the pressure goes down. Boyle's law has an equation that goes with it, and that equation is P1 V1 equal to P2 V2. So let's take a look at a potential problem for Boyle's law. Okay, and let's say that we have, I'm actually going to just sort of make this up as we go. All right, a sample of gas at 1.32 atmospheres and 16.4 liters is compressed to 7.21 liters. What is the resulting pressure? Okay. So what we'll do is we'll come in here and we'll say, okay, we have a sample of gas at 1.32 atmospheres and 16.4 liters. So that P1 is right here, 1.32 atmospheres. And our V1 is right here, 16.4 liters. And we have a V2 here, 7.21 liters. And we're looking for this P2 right here, and that's the resulting pressure. So that's just going to help you identify what we're working with. All right, so let's go ahead and then fill this in. And so we can see we have 1.32 atmospheres times 16.4 liters, and that's going to be equal to P2 times 7.21 liters. Okay, and just to help you out with the math a little bit, that means that P2 is equal to, actually, instead of this, let me go ahead and show it to you sort of as an algebra thing. Okay. Okay, so that means that we divide both sides by 7.21 liters. Okay. And we'll get a P2 value equal to 1.32 times 16.4 divided by 7.21. And we get a resulting final pressure. You can see we have three significant figures all the way through this of 3.00 atmospheres. Okay. And then we want to check. Remember that we have an inverse relationship between pressure and volume for Boyle's law. Okay, and so if that means that, see how the volume is going down, we're going from 16.4 down to 7.21, that means that the pressure has to go up. So I'm going to say, oh, it went from 1.32 to 3.0. And that is kind of you know, that's the way we check to make sure that we did this correctly, and we did. So there's Boyle's law. Okay, now let's take a look at our next gas law, and the next gas law that we're going to talk about is Charles's law. Okay, now Charles's law, we use Charles's law when volume and temperature are changing and everything else is constant. Okay, well that means pressure and number of moles are constant. And when we say number of moles, we really just mean quantity. We mean that we have a sealed system and none of our gas is escaping and no additional gas is entering. Okay, so Charles' law, want to make sure that I say everything. Okay, now remember from our first slide here that temperature must be in kelvins. And that's because Celsius has a 0 point and then it has a negative scale as well as a positive scale. And that won't work for this kind of mathematics. So we have to be in kelvins because kelvins do not have any negative values. Okay, so with Charles's law, we have a direct proportionality. So volume and temperature are directly proportional. Okay, so what does that mean? That means that volume goes up when temperature goes up. So they increase in the same direction. Okay, then the equation that we're going to use for that is V1 over T1 equal to V2 over T2. And again, our temperature has to be in kelvins. Okay, so let's go ahead and write out a problem for Charles's law. Now remember, our volume, temperature are going to be changing. Okay, pressure and number of moles are constant. So let's say that we have a 70-liter tire. That's not good. Sometimes when I start making things up, it doesn't make any sense. Let's just say this. A gas sample at 70 degrees Celsius has a volume of 29 liters. What will be the volume when the gas is cooled to negative 14 degrees Celsius? Okay. All right, so this is a good Charles's law problem. Okay, let's take a look at it. Here we have V1, and here is our initial volume for V1. And here we have T1, and here is the initial temperature for our T1. Okay, here we have T2, and here is our final temperature. And then last but not least, we are looking for V2, and we know that because it says what will be the volume. Okay, so that's what we're solving for. Now, before I can do anything here, I have to convert these. So I take that 70 plus 273.15, and I'll go ahead and just find significant figures later. 343.15 kelvins. And then I'll take this negative 14 and add that to 273.15. And here I get 259.15. Okay, so now I've converted to kelvins and I can do my math. So here I have V1 over T1. So 29.0 liters over 343.15 kelvins is equal to V2, which I'm solving for, times 259.15. Okay, now I'm going to use cross multiplication to solve this problem, and that will solve for any kind of a proportion like this. Okay, and what you do is you isolate your variable, you multiply by what's in the circle, and divide by what's left over. So V2 is equal to 29 times 259.15 divided by 343.15. Okay, and then I'm going to type that into my calculator. Okay, and again, I'm just going to verify this, that here I can see that my temperature has gone down, which means that my volume needs to also have gone down. And I have 3 significant figures that I'm working with here, so this becomes 21.9 liters. And I see that it did in fact decrease, so that's my check. Okay. Now, the next law that we're going to look at is Avogadro's law. And we learned about Avogadro's law, Avogadro's hypothesis, back in chapter 2 at the beginning of the semester. Okay, well, let's take a look at what the math for Avogadro's law is. Now, remember that Avogadro's law deals with our quantity and our volume, our number of gas particles and the volume of those gas particles. So what we can say is that the volume of a gas is proportional to our number of moles. And the variable used for number of moles is N. So that means that volume increases as our number of moles increase. And that's what we had learned back in chapter 2 as well. The math for this problem would be, I always write it backwards, N1 over V1 is equal to N2 over V2. If you're watching videos or something and you see it the other way, V1 over N1 is equal to V2 over N2, that's totally fine. It doesn't matter which side the proportion is on. Okay, so now let's think about what kind of a problem we might see out of this kind of a problem. Okay, so this is kind of an interesting one. Let's say that we have, well, remember when we were learning Avogadro's hypothesis and we said that 2 moles of hydrogen gas plus 1 mole of oxygen gas yields, you know what, this is fine, 2 moles of water vapor. Okay, or we could say that, I'm thinking, or we could say that 1 mole of nitrogen plus 3 moles of hydrogen yields 2 moles of ammonia. Oh, I like this one even better. So these are a couple of examples of some balanced gas equations. Okay, let's take a look then at what we're working with here. Okay, so you can see these values here, okay, and this is very different from what's in the slide, so make sure that you look at what's in the slide as well, but I want to show this because I think this is going to help you in your recitation. Okay, let's say that we know that we have, I feel like this is getting complicated. Let's do a couple of them. Okay, so let's say that we have 15 liters of nitrogen, and we want to know then how many liters of ammonia that we can make and how many liters of hydrogen gas will be paired with it. Okay, so this is very different from the one that's in the slides, but usually people understand the one that's in the slides pretty well. So this is a little bit more like what you're going to end up doing in recitation. So what Avogadro's law is directly saying is that we can compare this to our moles. So basically, if we have 1 mole of nitrogen goes with 15 liters, then we can actually look here and say, well, then 3 moles of hydrogen will be 45 liters. Does that make sense? So what I've done here is it's just, I said, oh, well, 1 times 3 is 3, therefore 15 times 3 is 45. So if 1 mole is 15 liters at the temperature and the pressure that we're at, then we need 45 liters of our hydrogen. And we can do it again. We can say that if 1 mole of nitrogen, if 1 mole of nitrogen goes with 15 liters and we'll make 2 moles of ammonia, so this was our nitrogen and this was our ammonia, then that means, because I said 1 times 2 is 2, then this would be times 2 is 30 liters of ammonia. So, and again, this is a very different kind of problem from what's in the slides, but I think it's really useful to see that you can use Avogadro's law to link the coefficients in a balanced equation to the volume directly. Okay, the next one that we're going to look at here is called the ideal gas law. Now, the ideal gas law is not looking at a system that's changing. So we're actually going to say that there, nothing is changing. And so we're going to look at a bunch of different things, and it's PV equals nRT. So what do each one of these things mean? T is temperature in kelvins, very important. P is pressure in atmospheres. So if you're given a pressure in anything other than atmospheres, you're going to have to convert it first. V is volume, and it has to be in liters. N is our quantity, and it's in moles. And what that means is that if you're given a quantity in grams, you have to convert that to moles first using a molar mass. Okay, now last but not least, let's look at why we have to have everything in these. And this is because our R value here is the ideal gas constant. And the ideal gas constant, and you'll see this in different places. I want you to use this one because it has 4 significant figures. It's 0.08206. And the units are liter atmosphere per mole Kelvin. Okay, so let's take a look at this. Now, this ideal gas constant, that is not ever going to change. Now, I don't want to make this one up because it might not work. So let's go ahead and use something. I'm going to sort of use something that's here, but I'm only going to change a little bit. Okay, let's say that we have a 304 liter tank that contains 1.07 kilograms of oxygen gas. At 24.8 degrees Celsius. And I want to know what is the pressure. In our tank. Okay, so before we can do anything, we have to make sure that all of our variables are in the format that we need. So first of all, it said volume in liters. And okay, well that one's easy because it's in liters. Check. Okay, now the next thing is we had our temperature in kelvins. And I see here that I have temperature in Celsius. So now I need to convert that. So 24.8 plus 273.15. Okay, and that gives me 297.95 kelvins. Okay, now I need my quantity in number of moles. And it tells me that I have 1.07 kilograms of oxygen gas. Now I can't use that at all. I need to do a couple of things with this. And that's that I need to convert my kilograms to grams, and then I need to find my moles of oxygen gas. Okay, so I have 1.07 kilograms times 1,000 grams per kilogram. Okay, so that means that I have 1,070 grams of oxygen gas. Okay, now I can say, okay, well, I know that oxygen gas is 15.999 times 2, or 31.998 grams of oxygen gas per mole. Okay, so that means that I can take 1,070 times divided by 31.998. Okay, and I can have 3 significant figures, and so I get 33.4 moles. Okay, now I can work my problem. So first of all, pressure is what I'm looking for. Volume is 304 liters equals my number of moles, 33.4 moles, times my ideal gas constant, 0.08206. times my temperature in kelvins, 297.95. So then if I'm going to do my algebra, I'm going to isolate P by dividing both sides by 304. And I will get that my pressure is equal to 33.4 times 0.08206 times 297.95 equals, and then I'm going to divide that by 304. And I'm going to get a pressure of 2.69 atmospheres. okay? And that is one example of an ideal gas law problem. So you can see that there are a lot of different pieces in this, okay? There's one more that we'll do, and that is the combined gas law. There's a couple more that we sometimes see, and I'm going to give them both to you here. The combined gas law is P1 V1 over T1 equal to P2 V2 over T2. And sometimes you'll also see a pressure temperature law, and they just call it pressure temperature law, of P1 over T1 equal to P2 over T2. So you might wonder where all of these laws come from. All right, so let me go ahead and show you. So this might be stressful for some of you, but for some of you who like math, you're gonna be like, oh, that's great, I don't have to think about any gas laws. Well, yes, there's the whole thing about how you really don't need any gas laws as long as you understand the ideal gas law. What the ideal gas law is saying, PV, hang on. PV equals nRT. Well, this R value is exactly the same for every gas sample, okay? So what that means is that if we could solve for R, and we could say then that PV over NT is equal to R. What that means is that for any set of conditions, you could say P1 V1 over N1 T1 is equal to R, and then you could say P2 V2 over N2 T2 is also equal to R. And then what you could do is you could cross out anything constant. So for example, in Charles's law, we have volume and temperature changing together, and we assume that pressure and number of moles aren't changing. So once you cross out anything that's held constant, you're left with Charles's law. Now, if that works for you, great. If it stresses you out, don't worry about it, okay? And that is actually the end of the first part of chapter 5. I'll see you in recitation.